Hello everyone, I am Dr. PSV Shanmukhi, Associate Professor, Department of Physics, Aditya University. Now I am going to explain about the Hall effect in semiconductors. At the end of this lecture, the student will able to understand the concept of Hall effect in semiconductors, and he can derive the Hall voltage expression, Hall quotient expression also. Now coming to the Hall effect. When a current carrying conductor or a semiconductor is subjected to a transverse magnetic field, then a voltage is developed perpendicular to both current and magnetic field directions. Such voltage is called Hall voltage and the phenomenon is called Hall effect. Say, observe this diagram. Say this is a semiconductor slab. This is a semiconductor slab. So whose width is given by W. The thickness of the slab is given by T, say. Now this is carrying current along x direction. Along x direction, this is carrying current I, say. So this is subjected to a transverse magnetic field. A magnetic field is applied along z direction. In such a case, voltage is developed perpendicular to both current and magnetic field directions, that is z direction. That developed voltage is called Hall voltage and the phenomenon is called Hall effect. Once again coming to the definition, when a semiconductor slab, current carrying semiconductor slab is subjected to a transverse magnetic field, then voltage is developed perpendicular to both current and magnetic field directions. That developed voltage is called Hall voltage and the phenomenon is called Hall effect. So now to derive the expression for the Hall voltage and later the Hall quotient, now let us consider this kind of a semiconductor slab whose width is given by W and the thickness is T, carrying the current along x direction like this. Generally, when the current is passing along x direction, actually at any temperature T, suppose constant temperature, there are some electrons and the holes in a semiconductor slab. The carriers are moving along x direction. Current is along positive x direction, say, the holes are travelling along positive x direction, electrons are travelling along negative x direction, we can say. Now this is subjected to a transverse magnetic field. What is the transverse magnetic field effect? The transverse magnetic field will deviate the charged particles continuously. Suppose this is a transverse magnetic field. When the charged particle enters the transverse magnetic field, Lorentz force acts on that one, continuously it will be deviated, it will describe the circular path of radius r. After completing the semicircle, it will come out of the magnetic field. In other words, in the transverse magnetic field, the charged particle will describe a circular path, means continuously the charged particles will be deviated. Suppose the holes are deviated in the upward direction, electrons are deviated in the downward direction, say. After some time, what happens? Holes are accumulated on the upper surface and electrons are accumulated on the lower surface, say. Now the upper surface is becoming, it is resembling a positive plate, lower surface is resembling a negative plate. It is just like a parallel plate capacitor of width W. Automatically electric field is developed there, EH electric field, that is called Hall electric field. Voltage is developed there, denoted by VH, Hall voltage. Anyhow, first of all, in presence of transverse magnetic field, the Lorentz force is acting on the charged particle. It is given by F is equal to BeV. Actually, BE sin theta. In case of normal magnetic field, transverse magnetic field, theta 90 degrees, sin 90 is equal to 1. Therefore, F is equal to BeV we get. So, because of this Lorentz force, the charged particles are deviated, holes are deviated in the upward direction, electrons are deviated in the downward direction. After some time, the upper and lower surfaces are charged, means they are acting like parallel plate capacitors. In presence of parallel plate capacitors, again the charged particles will experience some force. So, what is the force experienced by the charged particle? It is given by F is equal to E into E. That is the force acting. Actually, because of Lorentz force, the holes are experiencing the force in the upward direction. Because of the negative plate, holes are experiencing the force in the downward direction. In the same way, electrons also we can expect the force. That means these two forces, say this is one force, this is the another force, second force, these forces are in the opposite direction. At equilibrium condition, these two forces must be equal, so that there would be no further accumulation of the charged particle. Again, the charged particles will travel in the same along x direction. So, at the equilibrium condition, we can write the Lagrange force is equal to the electrostatic force. Therefore, we can write this as BeV is equal to E into EH, or EH is equal to, actually the electric field, this is just like a parallel plate capacitor, E is equal to VH by D, we know that, or this D is nothing but W, say, no problem. So, EH is equal to VH by D, we can write. Therefore, what is VH? So, this VH by D is equal to BeV, we are writing. From this equation, VH is equal to BeV into D, where B is the applied magnetic field, E is the charge of the particle, D is the separation of the plates or the width of the specimen, V is the velocity. You can take W or D, no problem. Actually, the current density J is equal to NeV, the current density, where V is the drift velocity, say. Therefore, let us write the expression for the velocity, V is equal to J by Ne, or J is actually current density, current per unit area. So, I by A we can write I by A into Ne, or it is I by A means D into T. Actually, I am just taking this width of the specimen is D instead of W, that is D. Automatically, we can write I by dt into Ne. This is the velocity expression. Substitute this velocity expression in the Hall voltage formula. Vh is equal to Be into D into V. Therefore, we get Vh is equal to Bi by Ne into T. This is the expression for Hall voltage. So, where B is the applied magnetic field, I is the current, N is the electron density or holes density, E is the charge of the electron, and T is the thickness of the sample. So, out of these parameters, this Vh we can determine by connecting one voltmeter here. So, automatically from the experiment we can determine Vh. B applied magnetic field, we know how much current is passing, that also we know. Charge of the electron is known, T is the thickness of the sample known. By this expression we can determine the electron density or the holes density in a semiconductor slab. We can determine the electron density or holes density. Anyhow, this is the Hall voltage expression. Now, coming to Hall coefficient, there is another important parameter in this one, that is Hall coefficient. Actually, the Hall coefficient is defined as the Hall voltage developed per unit applied current density and unit applied magnetic field. Generally, we write this as Hall coefficient RH. It is equal to the Hall voltage developed VH divided by Jx into Bz we write, where VH is the Hall voltage developed, that is along y direction, Jx it is the current density along x direction we are applying, Bz the applied magnetic field along z direction. Now, substitute this VH Bi by Ne into T. So, you substitute this is Bi by Ne into T divided by J is equal to I by A means D into T into B. Substituting all these parameters, that B and B cancel, Bi cancel, then dt cancel, Ne into D. This is also, so this is all these parameters are cancelled except this one, that RH is equal to 1 by Ne, where N is the electron density, E is the charge of the carriers. So, in case of electrons, N is equal to -1. Suppose especially it is a p-type semiconductor, say, we can write RH is equal to plus 1 by Pe, where P is the holes density. That means, by the Hall coefficient, we can understand what is the type of the material, whether it is N-type semiconductor or p-type semiconductor. If Hall coefficient comes out to be negative, we say that the semiconductor is N-type semiconductor, electrons are the carriers there. If Hall coefficient is positive, we say that it is a p-type semiconductor and holes are the carriers there. So, from this Hall effect experiment, we can understand what is the type of the semiconductor and what is the carrier concentration we can determine. So coming to the summary of this one, in this Hall effect experiment, we have discussed what is the Hall effect, definition and the concept of Hall effect. When a semiconductor slab, current carrying semiconductor slab subjected to a transverse magnetic field, then voltage is developed perpendicular to both current and magnetic field directions. That developed voltage is called Hall voltage and the phenomenon is called Hall effect. And we determine the Hall voltage expression VH and the Hall quotient RH. So VH derivation we have derived of VH and the Hall quotient RH also we have derived. Okay, thank you.